Hey everyone, this is Dr. Calkins. Today we're going to do week 12, chapter 10, electron transfer and chemical reactions. So there's two major features of this one, and that's calculating oxidation states and then doing oxidation reduction reactions. So we're going to start with those student submitted questions, and the first one's number 3. Number 3 says, if potassium, carbon, and oxygen are together, what is the positive oxidation states? So if we remember the rules from page 124 in our lab, atoms are 0 in their elemental state. That's something that we've seen from the beginning of the semester. Oxygen's a -2, hydrogen's a +1. If you're in group 1, you're +1. If you're in group 2, you're +2. None of those are anything new since week 2 of our semester. Now in week 12, 10 weeks later, still the same. The charge of any ion by itself is the oxidation state. So in that case, charge and oxidation state are exactly the same. All oxidation states need to add up, and halogen's usually -1, which is what we'd expect being so close to the noble gases and gaining 1 electron. So most of those are ideas that we can use here, because if you notice in this example here, we have potassium. That's a group 1 metal, so that's going to be a +1, and there's 2 of them, so that's a +2 total. We have oxygen, which is a -2. That's the rule number 2 from page 124. There's 4 of those, so that is a -8. And really what we're doing is asking, what does carbon have to be here in order for a +2, this magic answer number that we're looking for, a -8 to balance, all to make this neutral compound with no overall charge. So the sum of the charges, which was rule number 7, has to add up to 0. So what number, +2, can completely balance, equal but opposite, a -8? It's going to be a +6. So +2 and a +6 can make a +8, and that will cancel with a -8, and that's what we want. We didn't need to solve it in this situation, we just needed to know who is positive. We see that potassium is positive by rule. That was rule number 4. Group 1 is always a +1. When it's attached to other partners, not in its elemental form, then it'd be 0. And then now we see that carbon has to be positive to make up for all that negative on the oxygens. So in this case, we have both potassium and carbon. Potassium's a +1, and if you recognize that there was 2 carbons that are +6 each, that would have been a +3 per carbon. And that's number 3. So number 5, a little bit tougher because now it's saying who is more positive in oxidation state. So to be more positive, you have to lose electrons. So when they say more positive, that's really saying who is oxidized, because if you're oxidized, you're losing electrons, you're going to become more positive as a result. So this is just a fancy way of saying who's oxidized. In order to understand who's oxidized, you have to do an oxidation reduction reaction. So as we try one of these, it might be easier to just use a blank sheet of paper and think about it. So different from up here, we might have to think about charges as we think about some of these examples, but when we do half reactions, we just pick all the elements, iron to iron, we have oxygen to oxygen, and we have carbon to carbon. We need to know in this little story, where did they start, where did they finish? If you think of Fe2O3, you can remember that you can reverse cross charges, and that tells you that iron starts at a +3 in iron 3 oxide, and oxygen, as expected, is a -2. That's rule number 2. Over here we see oxygen being a -2 as well, and there's only 1 carbon with it. If there's only 1 carbon with it, that means it has to be equal but opposite with a +2. So carbon starts out as a +2. Notice we do have 3 ions here, at least 3 charged species. One of these is not going to change. It's going to be a spectator. We're about to find out who, because after the arrow, what happens is iron is by itself. Elements are 0 in their oxidation state and their elemental state. That's rule number 1. Oxygen is itself with a partner, so it's going to be a -2. There's 2 -2s, that's a -4, so carbon's going to be a +4 to balance. So oxygen stayed the same, carbon went to a +4 because it has now an extra oxygen. So this is our spectator ion. We can get rid of it. It didn't change, it's just there. enjoying the ride. Now we have to decide who became more positive. Well, that's a little more obvious in this one because this one was +2 to +4. So carbon is the answer there. For practice though, how does it become +2 to +4? It loses 2 electrons. 2 negative and 4 positive equal +2. Same thing would happen up here, but differently. If you have 3 negative electrons, 3 negative and 3 positive will equal 0. So you can always check your work in oxidation reduction reactions. For practice with Leo-Gur, remember loss of electrons is oxidation. So here we have oxidized in the reducing agent. And up here, this is the gain of electrons going into your arrow versus losses after. So here's the loss, here's the gain. And again, this would be gain for Gur, so G equals R in the end of Gur, which is reduced in the oxidizing agent. So that's something they didn't ask for, but it's good practice. You'll see a lot of that in our experiment 19. Number 7 is just a definition. Number 7 is what is reduction. And remember Gur, Leo says Gur. Gain of electrons is reduction. So letter B, a little bit easier one than the last 2. Number 9, a little bit tougher. Number 9 is going to have the same issue. So when we do number 9, we have to do the exact same thing we did with number 5 and think about before and after, but uniquely in this one, we have a sharing of lead as a product. So let's write these out. We have lead goes to lead. Specifically, this is the first lead, which is elemental lead with no charge. This is the battery you'll find in your car, lead storage battery, or your boat maybe. Then we have this lead with 2 oxygens. So remember, oxygen's a -2, so if this is 2 -2s, that's a -4. Lead's going to be a +4, that's a plumbic ion. We have oxygens and we have hydrogens. Oxygens, anytime they're in a compound, is a -2, that never changes. Hydrogen specifically says it's a +1, and that was rule number 3. That's just acid in this case. We still have hydrogen, we still have sulfate, but notice sulfate and sulfate never change, so we're going to cut to the chase there and just say sulfate stays sulfate. It's a spectator ion, so don't worry about it either. We're cheating a little bit there, but if you recognize them exactly in the same kind of ionic forms before and after, definitely get rid of them and save you some time. Hydrogen's still a +1 with hydrogen sulfate there. Here we have sulfate, which is a -2, so lead became a +2, but when lead becomes a +2, there's only one lead, so both of those are +2. That's the uniqueness. They're sharing this lead sulfate lead as a product. So that's the most unique feature of this particular reaction, because the oxygen's still -2, still -2 in a compound. That was rule number 2. And hydrogen still in a compound, just like it was in a compound here, and just like it was by itself there, it was still a +1. So those are more spectators. Get rid of those as well. Not important. So really what makes your lead battery work in your car is lead. Lead metal and lead oxide are the ones that are trading electrons. So in this case they say reducing agent. Remember, agent is the opposite. So if you're a reducing agent, you're also oxidized. So we need to figure out who is the loser, the Leo. The only way to become positive is to lose electrons. That's the opposite of what your gut feeling wants to think. If you were to put electrons over here, negative and 0 will not make positive. Only 2 negative and 2 positive will equal 0. This is a loss, that's a Leo. Loss of oxidation, or loss of electrons is oxidation, and that is the reducing agent, which is what they want, so we want lead metal. So it's a tough problem because it shares the +2 plumbous ion as a product. Those 2 electrons are then gained by the lead oxide. So 2 negative, +4 equals a +2. That's a gain. Gain is Gur, R for reduced, and the oxidizing agent. So once you find one, you get the other. Remember, we never choose products even though there's answers. So even though there's A, B, C, and D kind of answers, we're never choosing products ever for electron transfer reactions. So you usually only have 2 choices in your homework, not 4, because 2 are products and 2 can be thrown out. Very similar is number 10, but a whole lot quicker, a whole lot easier compared to number 9. This one says oxidizing agents. Remember, agents, just like in movies, those are double agents, so think oxidizing agent is reduced. So if you're reduced, you're causing somebody else to be oxidized. That's why you're an oxidizing agent. So again, pick them out. We have an iron, we have a copper, and then we have a nitrate. Again, I'm going to cheat here with nitrate because you'll notice the nitrate stays nitrate. So that's your spectator ion. But iron and copper change, and we're going to need to see how. A little bit easier to see how here because if you reverse these charges, copper was a +2, iron was by itself. By itself is no charge, that's rule number 1. But notice copper ends up by itself, that's no charge, and just like we reversed the charges there, +2. So you can definitely see here that they switched. And that's a characteristic process of single replacement. So then they say, who's the oxidizing agent? Remember, that's also reduced. So if you have 0 to +2, so 0 to +2, just like before, we have 2 electrons. We saw that with lead a moment ago. +2 and -2 equals 0. That's what we want. This is a loss of electrons. Loss is a LEO. LEO is LEO, so loss of electrons is oxidized and the reducing agent. Remember, agents are opposite. Those 2 electrons are then brought over and absorbed by the copper ions, and they become copper metal. So notice 2 negative and 2 positive equals 0. Very similar to what we would have done with nuclear chem, looking at those kinds of mass numbers. Here we're looking at charges. So similar but different. Here we have a gain. Gain is GER, G-E-R. The R stands for reduced, and the oxidation is the oxidizing agent, which is exactly what they want. We want the copper +2 ion, which is letter C. Notice copper was a choice, but copper is a product, so get rid of that one. Iron was the other option that was actually a legitimate choice, but it was oxidized, not the oxidizing agent. And then nitrate was our spectator ion. So again, watch out for products. Products are never answers because that's after the electrons have been transferred. Moving on to page 12, number 12 on page 2. What we see here is the Electro-Motive Series. So this is just the series that tells us when things will lose electrons and when they don't. So you have one of those in your lab book. The one in your lab book, I believe, is also in experiment 19 on page 128. So you'll see that one there. Lithium, the most active metal, is the easiest to lose, so it's easiest to oxidize. And then as you get to the bottom, you lose electrons the least easy. That means you're more likely to gain them, so you're going to be the easiest to reduce at the bottom. So number 12, they say consult the series, predict what will happen if an iron nail, remember iron nail just means Fe metal, no charge. Rule number 1 for oxidation states elements are always 0. And then they say with a tin ion. So remember, you need to look for the ion first, and then look to the metal second and say, is it higher? If it's higher on the list, it works, and if it's not, it won't work. So as we look, remember to find the ion first. That's the one that would be married in our home wrecker analogy. So let's see if it works first. We need 10 plus 2, so 10's down here. Would it be better to run off into the sunset with iron? It's up here. So the answer would be yes. This would be a working single replacement reaction. So what would happen then? What would happen if we were to add iron with 10 plus 2, and the spectator ions are relevant here? They would switch. We would get iron plus 2 and kick 10 to the curb. Again, spectator iron relevant, whether it's chloride or nitrate or anything else, doesn't really matter. So what happens to Fe? It goes to plus 2. What happened to 10 plus 2? It went to 10 metal. So again, elements by themselves have a 0 charge. So if you become plus 2, it's because you lose 2. We saw that a couple times now. 2 electrons are absorbed by the +2 ion to make the 0 charge element. Electrons in is a gain, that's a GER, that's reduced in the oxidizing agent. Iron goes to +2 by losing electrons. Losers are LEOs. O stands for oxidize, that's also the reducing agent. Never choose products, even other choices. So let's look for one of these ideas in our question. It says iron will be oxidized. So, yep, so that works. Tin will be further oxidized, that's wrong. Nothing will happen, well, definitely iron was higher, more active, so it will work. Iron will be reduced, well, it is the reducing agent, but agents are opposite, it's actually oxidized, so letter A. So we look lower on the page, we get to a little quicker types of problems. Number 18 talks about which element may not have an oxidation state of -1. A lot of these are based on rules. Halogens we said would be -1 by rule, and both of those are halogens. Hydrogen can be a +1 or -1. -1 would be if it would be like helium, that would be the hydride ion. Who's definitely never a +1 is sodium. Metals like to become positive, never negative. Sodium likes to be a +1. And that was, I think, rule number 4 from earlier on our page 124. Group 1s are always +1s, was our rule. Number 19. Number 19 talks about which element can have a -4. Carbon can be a +4 or -4 given its position in the periodic table. So its location tells us that. You can have -1, -2, -3, -4, or +1, +2, +3, +4, all the way back to helium. So there's our answer. Magnesium, only a +2, it's in group 2. Aluminum, +3, has 13 electrons, goes back to neon with 10 electrons. Chlorine has 17, goes forward to 18, that's a -1. So based on those locations, we can go back to chapter 2 material and say -1 is what chlorine wants. Aluminum from 13, it's easier to go back to 12 to 11, and then eventually back to neon with 10, becoming that +3. Magnesium, very similar, goes back 2, and that's going to take you back to neon. It's too much work to go forward across the periodic table for metals like that. So here, who becomes +4, and that can be a carbon. It can also be a -4. The +4s that we're typically seeing are, say, lead and tin, but they're in the same family. As you look at number 20, fancy words tend to mess up students. Iso means same in this case. Electronic just means electrons. So who has not the same electrons? So if we look at the periodic table, we can cheat off of a couple of these. Fluorine is number 9. So 9 electrons. Neon, right next to it, number 10, so 10 electrons. Magnesium has 12, but if you take away 2, you go back to neon that only has 10, so now we know that fluorine is different. Let's just practice oxygen. Oxygen's a -2, so we're going to gain 2, but oxygen has 8. When it gains 2, it's just like neon, and just like magnesium, +2. Those share the same electrons, so the one that doesn't have the same number of electrons is fluorine with only 9. Number 23 looks scary. It's got this antimony-based ion, but it shouldn't be too scary because it says the sum of the oxidation states is the charge, and the charge is a -1. So that was one of our rules. It happens to be rule number 7. So the charge is the sum of all the atoms present in the ion. So -1. So don't think about that one too tough. At least too much. Number 24 says, what is the charge of nitrogen in the ammonium ion? Remember, there's lots of ways to do these kinds of problems. The one that I did on the front page, I did kind of in the shortcut kind of manner. Ammonium is NH4 +1. So basically, this atom and this atom need to equal +1. Well, if we know that 4 hydrogens at +1 each, that's rule number 3 on page 124 of your lab book. That's a positive 4. So if positive 4 equals positive 1, what's missing is the charge of nitrogen that forces the positive 4 to feel like a positive 1 overall. The only number that mathematically works there would be a negative 3, which is nitrogen's favorite charge. So negative 3, when you add 4, you still get a positive 1. In our lab book, what we also teach you is you can take nitrogen, you can add 4 hydrogens, and it all equals positive 1. When you plug in those rules, you say nitrogen plus 4 positive 1s equals a positive 1. If this is a positive 4, we need to subtract 4 on both sides so that these cancel. Nitrogen equals the same kind of math that we kind of did above, but in reverse. A negative 4 and a positive 1 equals a negative 3. So either way, we can get to that kind of answer algebraically or maybe in our head for some other students. So for 24 there, we're looking for nitrogen's favorite charge because it is the bully at a negative 3. Moving along, we have number 28. 28 says, which of the following is true about the reaction? So another Leo-Gur kind of problem. So in this reaction we have magnesium goes to magnesium, oxygen goes to oxygen. So lots of practice of these in the homework as well as the lab. Notice they're by themselves, those are elements, that's rule number 1. It doesn't matter if you put a 2 here and a 2 here to balance, it's not going to change the answer. Over here, oxygen's in a compound, but both of these are rules. Group 2 is plus 2 is rule number 5 of our list, and oxygen is negative 2, that's rule number 2 of our list. So notice magnesium became a plus 2 because it lost 2. Oxygen was more than happy to take those electrons and become a negative 2. Sure, if there's 2 atoms and there's 2 negative 2s, that might be a 4 electrons. But what really matters is the electrons in front is a gain, the electrons after is a loss. Loss is Leo, O for oxidation and reducing agent. Gain is Gur, R for reduced and the oxidizing agent, so you can get rid of products, remember. Oxygen gas happens to be one of the best oxidizing agents, go figure. So let's look what happened. Oxygen is reduced. Well, yes, that's exactly what happened. It's also the oxidizing agent. Magnesium is oxidized, so both of those so far, so good. The oxidation state of magnesium is a plus 2. Well, no duh, because it's in group 2. All the above then fits just fine. Number 29 says, what's true about this reaction? Well, this one's based on the galvanic cell battery that you would see, at least it's very similar to it. What's important about this reaction is zinc metal is kind of gray. Copper chloride solution is blue. So what happens here is zinc chloride solution forms, and that's clear, and copper metal, which is just like a penny, is kind of brownish in color. So that's what it would look like if you were to zoom into some of those pictures. So in A it says the solution will turn blue. Well, it's already blue, so that's not it. The solution will turn from blue to light blue. That's going to happen as copper plus 2 ions leave solution, so definitely that one's going to work. Gray zinc powder will disappear. That's because it was a 0, not soluble in water, gray, but when it becomes water soluble as an ion, it becomes clear, and it will look like it disappears even though it's still in solution. So in this case, B and C are both correct. Number 30, they say which one transfers the most number of electrons. So let's look at magnesium. Like what we saw above in number 28, this is a magnesium goes to magnesium plus 2, so that's 2 electrons. Oxygen goes to negative 2, which is still 2 electrons each atom. Copper with 1 chlorine, copper with 2, so that just means copper went from a 1 to a 2, so that's only 1 electron because copper was a plus 1 and it went to a plus 2. So far the winner is A. Over here, a little bit tougher, we have to do the math, and these answers are also on the matching in the back section. I'm going to go quickly on these, I'll go slower on the ones later in the matching section. Sodium is a plus 1, we have 2 oxygens. 2 times a negative 2 is a negative 4, so chlorine needs to be a plus 3 in the chloride ion. Same thing over here, +1, but now we have 4 oxygens, that's a -8. What's missing is a +7, so that one lost 4 electrons. So far, the new winner. In hypochlorite, we have 1 of each, so +1 and a -2 means chlorine is a +1. Over here with sodium chlorite, we did this one over here earlier, +1, -4, because that's 2 -2s. What's missing is a +3. So if you go from 1 to a 3, that's only 2 electrons lost. So the winner is the one that transferred the most with 4 electrons. Also the one with the most number of oxygens. And number 32, what's important about this one is the way that it's written, the metal, and then the ion. So when you see that, just look for the metal and then the ion. So it's very specific to the actual battery. Copper zinc batteries actually won't work because copper metal is less active than zinc ions. So number 33, it says the oxidizing agent is, well, we can get rid of 2 choices in both of these because there is no such thing as a oxidation reaction or a reduction reaction. You can't have one without the other. So that eliminates 2 of our choices, so none of this would make sense because there is no such thing as a reduction reaction or an oxidation reaction. You can't have one without the other. Remember, agents are opposites, so the oxidizing agent is reduced. So bingo. The reducing agent is opposite, so it is oxidized, but it has to be in a redox reaction. So look for oxidized in a redox. So they have to be redox to be an answer because you can't have one without the other. So get rid of those other choices. I just made those up to confuse you. In 35, another Leo-Ver kind of problem, but I'll cut to the chase. This one's also in your lab book. Hydrogen's a +1 in a compound that was one of our rules. Happened to be rule number 3. Stays +1, so same, spectator. Oxygen was a -2, but it stays a -2, spectator. Carbon is a +4 because 2 oxygens would make a -4. But even over here with a -6 on the 3 oxygens, hydrogen's at a +2, you're still at a there's a +4 there, and even carbon didn't change, so all 3 were spectators. So this is an example where nobody changes, so nobody's oxidized or reduced. And I can very quickly get us through the next one as well, because if you have ions that trade places, this is double replacement. And what we should know about double replacement is those were questions we saw in week 10 for a reason. They make precipitates or water. Here we made water. And anytime you have double replacement, you're trading ions, not electrons, so that one's a definite. Nobody changes. So hydrogen stays +1, sulfur stays at a +6, oxygen stays at a -2, and then those aluminum stay at +3s. 37, also a big, long, torturous problem. So we need to write this one out because it's going to take some effort. So we need a before and after for I, for H, for O, and for Cl. So definitely 2 of these are spectators. Iodine starts out as the elemental form. Whether you put a 2 here and a 2 here doesn't change anything. Hydrogen in a compound is a +1, that was one of our rules. Oxygen in a compound is a -2, that's a different rule. Same set of rules overall. Chlorine is by itself, that's an element. Whether you put a 2 here and a 2 here doesn't change the answer either. As we go over here, this I here was from HiO3, so H is a plus. We have 3 oxygens and a -6. That's 3 times a -2 each. What's missing is a +5. I did that in my head. It might take a little bit longer at home to do that, but that's cutting to the chase. Save a little time. Hydrogen's still a +1 because it's still in a compound in both cases, so spectator. Oxygen still in a compound, still -2, also a spectator. Hydrogen is a +1, so chlorine has to be a -1. Turns out that's the Halide Rule. So iodine started at a 0, went to a positive 5 by losing 5 electrons, 5 negative, 5 positive equals 0. Always be able to check your work. Takes 1 electron per atom, so whether this is a 2 and you make this a 10 up there, doesn't really matter. What's important is these electrons are gained. That's reduced in the oxidizing agent. These electrons are lost. Lost is a Leo. O for oxidized. This is oxidized. Opposite agent is a reducing agent. Let's look at our choices. They say, who is the oxidizing agent? Oxidizing agent is the same thing that is reduced, that is chlorine. The element, not the ion, but the ion wasn't a choice either way. All right, 38. What is the equation for rust? This is a Chevy reaction. Rust takes iron and oxygen. No copper, let's get rid of that. No manganese, even though that's in some steel. So now it's really a matter of iron and oxygen or iron and oxygen, so both of these are relatively good examples. Rust is actually iron 3 oxide, so that's the answer there. Notice water is before and after, and that's because water accelerates rust. That's why vehicles rust a lot in, say, Missouri, and even further up north. Well, very common to get rusty vehicles up north because there's so much water from all the snow and rain throughout the year. But very little rust in the desert, so water can accelerate rust based on hydrogen's position to iron on the activity series. Anyway, number 39 says, which of the following is an oxidation reduction reaction? Well, let's get rid of examples that are double replacement. So double replacements are going to have 2 married couples, and then they're going to switch. So get rid of those. These are double replacements, and those should never be answers ever for redox reactions. So then we have a choice of combustion or combination. Well, I'll tell you right now that combustion has to be redox every time because oxygen starts out at elemental form and it goes to that -2 per atom in either carbon dioxide or water. So it's going to be a gainer of 2 electrons in either situation. So it's going to be the answer. Briefly though, let's talk about why C is not. Calcium is a +2, but it stays a +2, so spectator. Oxygen's a -2, stays a -2, because it's in a compound, even over here it's still a -2, so if 2 do not change, the third can't change. And that's because carbon is a +4, because 2 oxygens is a -4. 3 oxygens is a -6 total, but again with calcium being a +2, it stays a +4, so nobody changes, and that's why it's not a redox. Number 40, a little bit more specific to a week 10 question, which one is combustion? To be combustion, you have to have O2, CO2, and water no matter what. These are double replacements. Saw those above. And this one was a combination because you're combining into one product. So here are those. Review from 2 weeks ago. Number 43 says the magnesium +2 ion owns 10 electrons. So let's look at it on the periodic table. Magnesium is number 12, so it owns 12 in the beginning. But if it's a +2, it's because it loses 1 to be like sodium. But it really likes to lose 2 to be like neon, which has 10. So true, magnesium loves 10 because it loves to be noble gas-like. In this case, neon. Number 49 says the lowest oxidation state of sulfur. Well, we can do this for both this question and the previous one because we know the limits of any atom because they're noble gases. So we know sulfur can go forward. When it goes forward, that's going to be a -2. So -2 is what we told you should happen because it goes 1, it goes 2, it goes to be like argon. That's what's easiest. But sometimes life gives you lemons and other times it gives you lemonade. So what can happen if sulfur is bullied specifically by, say, oxygen, it can go back a +1, +2, +3, +4, +5, and then eventually back here to +6. So we know now, based on the location of the periodic table, that sulfur can go forward to -2 or back all the way to the other noble gas at a +6. We know it has 6 valence electrons, it would lose all of those. So then we're worried about, is sulfide the lowest oxidation state? Well, the problem with this question that is now false is because the lowest is a -2. And when sulfur is a -2, we call that sulfide, not sulfite, IDE, not IT. Sulfide is SO3 -2. 3 oxygens is a -6. This would be a +4. That's nowhere near its lowest charge. That's very close to its highest charge. So sulfide, sulfur as a +4 because a +4 and a -6 equal a -2 charge. Again, those oxygens -2 each, but there's 3 of them. So again, if you wanted to go back to 48, which wasn't asked, but the same idea, sulfate is SO4 -2. The highest oxidation state was, that was supposed to be a +6. +6, and sure enough here, with 4, -2 oxygens at a -8, sulfur will be a +6, so this one would have been true because it would be the highest +6 kind of charge. I just forgot to make that a positive. I wrote it earlier. Number 52 says the cathode is the electrode where reduction occurs. Well, cats have positive charge, and if you have a positive charge, you're going to be gaining electrons. If you're positive, you're going to attract electrons from somebody else. So this is the positive side of the battery. This is where electrons come in, and if you're gaining electrons, GER says R for reduced. So true. The anode is where oxidation occurs. Number 54 is the last slide of PowerPoint. Even the one that I improved is still the last slide. And they attach magnesium, which is more active than the ship's hull, which is iron. So if we look on the activity series, what you'll notice about it is if your ship is made of iron, you can attach magnesium, which is higher on that list, so magnesium can oxidize, so iron doesn't have to. So do that with utility poles, with outboard motors, with boats, and with very large ships. They don't rust in the ocean because of all the water, not because of the salt. That is a myth. Number 55, bunch of practice using oxidation state, which is the entire front part of the experiment 19. Carbon and carbonate. So carbonate is CO3 -2. That just means that carbon plus 3 oxygens equals -2. To do all of these problems that are pretty much left, we need all these oxidation state rules from page 124 to help you. So here we have C equal -2. Carbon has no rule, so it's like X in algebra. Oxygen does have a rule, it's -2. So if you want a -6 to go away, you add 6. But when you do something to one side, you have to do it to both in algebra. So here we have a -2 and a +6, which makes a +4. So find +4 and you find the answer to this one. Nitrogen and sodium nitrite. So sodium nitrite is NaNO2. Notice this has no charge. So sodium plus nitrogen plus 2 oxygens equals 0. Now we have to solve it. But use the rules. One of the rules that we have is group 1 is a +1, and sodium is a +1 because it's in group 1. Nitrogen has no rule. Oxygen does. It's a -2 as long as it's not by itself in elemental form. So here we have some like terms. Let's combine those. We have this -4 and this +1, so that's going to make a -3 left over. Still equals 0. The only way to get rid of a -3 is to add a +3. Do one side, you do the other. Nitrogen is a +3. Remember, in these situations, you can check your work. This one would have been straight across and matching. You can always plug these back in. I didn't do that for the last example, but this one's a little bit easier to see. If we plug this back in, +3, +1, does it balance with 2 -2s? 2 -2s is a -4. And notice, it's a +1. +1 and a +3 is a +4, and a -4 balance to make 0 overall charge. Just write +1, not +4 for some weird reason. In any case, number 60, nitrogen and ammonia. This one's a little bit easier. We could actually cheat on this one a little bit. Ammonia is NH3. We know that 3 hydrogens would be a +1, and they have to balance. This is a -3. So -3 and a +3 cancel. You could also write this out. Nitrogen plus 3 hydrogens equals 0. Nitrogen plus 3 +1s equals 0. Subtract 3 on both sides. These cancel. Nitrogen still is -3. It just spends a few minutes of our life that we can never get back because of algebra. So now in 60, we're looking for nitrogen to get what it wants because it's the bully, not hydrogen, and it's going to be a -3. So do all the rest in a very similar fashion. Number 60 through 71 that's next. I was kind of surprised that students ask these questions, but they do every time, and it's because after they've been tortured to this entire homework problem set, they're like, how can these questions be so easy? Shouldn't they be tougher? So when we think about it in that context, it should just be, in this case, find a noble gas. If you have 10 electrons, that's basically saying who wants to be like neon? If you have 54, who wants to be like xenon? And if you have 18, who wants to be like argon? So this takes us back all the way to week 2. Just been so long, and because the rest of this homework is so hard, students just can't believe that I would put something easy on here. But in this case, it should be that easy just to find them. Magnesium, number 12. Who would it more than likely go to? Definitely who it's closest to. It's going to lose 2 and be like neon with only 10. Aluminum, it's number 13 on the periodic table. Would it rather go to 10 or 18? That's the only ones that are relatively close. Losing 3 is a whole lot easier than gaining 5, so it too is going to go to the nearest noble gas. Sodium, number 11. Definitely going to go to neon because losing 1 is easier than gaining 7 to go to 18. That's way too much work. Potassium is number 19. So if potassium is number 19, it has a choice to go to 54 to 18. Definitely losing 1 is a whole lot easier than gaining a whole bunch, or losing a tremendous amount. Going past a noble gas would be crazy. Cesium, definitely one of the biggest, and that's number 55. So losing 1, a lot like the same family member sodium above, takes it to the only answer that was not picked, and that's xenon. Very similar is 66 through 71. A lot of students can't believe I would give them a question that has such an easy answer after torturing you through those redox equations, but this one should be very fast. What is their favorite charge? Because remember, if you're by yourself, your oxidation state is your charge. There's no bullies when you're by yourself. So if aluminum has 13, because it's number 13 on the periodic table, it's going to love to lose 3 of those electrons to be like neon, the noble gas. Oxygen, number 8, it's going to love to gain 2 electrons, just like we'd expect all halogens to do. Barium, number 56 on the periodic table. The nearest noble gas is 54, so it's going to be a group 2. It's going to lose 2. Fluorine, it's got 9, it's going to want 10. The way to get there is to gain 1, like all halogens should do. Arsenic, arsenic has 33 electrons, it wants to go to 36. That's going to be gaining 3 like the nitrogen family should. And then sulfur, like all chalcogens, like oxygen, sulfur has 16, it wants 18 like argon, so it's going to gain 2, just like its family member above with the weird line that I didn't draw straight. So my OCD doesn't like that, but in any case, same answer, -2. Home stretch. You've been with me and haven't fell asleep after 40 minutes homework questions. I like to say it gets better, but all the other chapters are gutting and more math, so it'll probably be long videos from here on out, so just bear with the math. In this situation, we see the life of a chlorine atom. So let's cheat real quick and think about the life of the chlorine atom based on its position and kind of get a heads up of where we're headed. So here's chlorine. It can go forward and be a -1. It can be in its current location and be a 0. elemental. Or it can go back 1, 2, 3, 4, 5, 6, and eventually 7. Go all the way back and become a +7. So the life of a chlorine atom can be from a +7 to a -1, just like the choices. So chlorine as an element can be a 0, but it could be chloride. And then it can all the way down to chlorine +7. That's the life of a chlorine atom. So as we look at some choices, sodium chloride NaCl, a little bit easier than some of the rest. Sodium is a +1, so chlorine is a -1. That's because chlorine is the bully getting what it wants. And that's best case scenario for chlorine. Sodium hypochlorite, chloride, chlorate, perchlorate. I put these in order for a reason, because notice NaClO, NaClO2, NaClO3, NaClO4. In all situations, we have this +1 sodium. And in all situations, we have this -2 oxygen, but we have more of them. So this one's the quickest one because there's no multiple of oxygen. If you have a -2 and a +1, you need another +1 to make the 0 neutral compound. So +1 was the answer down here. So that's chlorine on its way to +7. But notice now we just add another oxygen. So now it's a +3 because now this is a -4 when you think of 2 times the -2. So that's just 1 oxygen more bullied. So now we have chloride going to +3. We add another oxygen, we go to a +5, and we go to a worst case scenario with 4 oxygens, that's a +7. Each time we add another -2, we're making chlorine feel another +2 more than it was previous. So notice those odd numbers. This is with 1 oxygen, 2 oxygens, 3 oxygens, and then 4 oxygens. Worst case scenario would be 4 oxygens, 4 bullies. That's terrible. Same thing kind of happens for nitrogen here. You can look at nitrogen on this same kind of periodic table and recognize what its possibilities are. You can go -1, -2, -3. So moving forward makes it that -3 we thought nitrogen would always do. It can go +1, +2, +3, +4, all the way back to helium, which would be +5. That would be worst case scenario, all the way back to helium. So nitrogen's life, elemental, would be 0. But we now know that it's going to go to a -3. Nitride would be most common. But we also see that it can also go down to a +5. Based on its location in the periodic table, it can lose all 5 valence electrons. So nitrogen gas, definitely, that's the 0. Nitride, IDE, that's the ion that we learned on exam 2. So those answers can be probably the quickest. Then just think about the bullies that oxygen has here. Sodium nitrite is NaNO2. Nitrate is NaNO3, that's the T4-3 ion. Sodium still a +1. Oxygen, 2 -2s is a -4. 3 -2s is a -6. Think about what's missing. What's missing is the oxidation state of nitrogen. To balance a -4, we need a +3 because this together would be a +4 and that would cancel. To get this to balance, we need a +5 because that would be a +6 and that cancels with a -6. So definitely more oxygens means more positive charge, less oxygens means less positive. So nitrogen's way to get to a +5 goes through a +3 that we saw with the nitrite. So hopefully the next chapters will be better. That's usually not the case, they get worse. Sorry for that, but that's math. And math and chemistry go hand in hand oftentimes, so see you next time.